All right, welcome everyone. Ooh, a little bit echoey. I am no longer coughing as much, still coughing some, but now you can hear my voice isn't quite 100%, so I apologize for that. But otherwise, feeling well. So today we need to finish up the final topic that is fair game for our upcoming exam, our upcoming test. And this is this stuff about divergence and curl. There's a strong overlap with the material that we did back in 16.3, which was about conservative vector fields and the fundamental theorem of line integrals. And so you probably felt some of that already in the pre-class video. But before we get too much into the specifics for today's math lesson, just a quick highlight and overview that, again, we have our test coming up this Thursday. It covers largely chapter 15 and, of course, the stuff that we're doing here in today's class. Of course, math builds on itself. So although certainly the focus of these questions will be on chapter 15 and 16.5, it doesn't mean necessarily that you completely forget, everything that came before it. But yeah, there'll be lots of integration in this upcoming test. Similar to our first online test, this one's, again, online. You have 60 minutes. And so again, you should be expecting, closer to maybe 12 problems in total. They are getting a little bit longer, as you're probably feeling with these triple integrals and whatnot. So I wouldn't be surprised if there was, 11 or 10. But if they were nice problems and, they were curated to be done quickly, okay, 12 would be reasonable still. But somewhere on that order, again, being like twice the length of a quiz. Again, you have quiz and exam revision assignments you could do to practice. We have a D2L practice test that you can use to practice. I have that checklist. Wednesday's class will be a review. And again, kind of we can go in here and I could showcase really quick, assuming D2L loads for me. So if we go under the test 2 content, that's unit 3 here. We have this online test 2 review in class, this PDF here. And similar to last time, you can vote and tell me which problems you want me to cover in Wednesday's class. All right, I think that's the majority of my administrative stuff. Quiz 6s are currently being graded. I think last I saw, maybe half of them or so were in. So that's still coming down the pipeline. But I've emphasized to our TAs and whatnot that, of course, with the upcoming exam, everyone's interested in getting those scores. So hopefully they're all done by tonight. Any questions about anything, administrative or otherwise, before we jump into our math for today? All right, well then. In the pre-class video, we talked about this new operator, this del operator, which is a vector made up of partial derivatives. So in the first component, partial derivative with respect to x, then y, then finally z. And if you apply this in clever ways to vector fields, you can get a couple of interesting things. So the first is, if you do a cross product, you get this thing, the curl of f. And you may remember, and we brought up here, right, for 16.3, this q sub x equaling p sub y, aka if this third component right here was 0, then we knew we had a conservative vector field, at least for 2 dimensionals, when you only had p's and q's. Of course, now we have r's. So when this was 0, it turns out, right, we could apply this fundamental theorem of line integrals. So this is one of the main uses of curl here, is that if you want to extend this to a 3D case, it is exactly that. You want the curl of f to be equal to 0. So there's that one kind of awkward Weber problem at the end of 16.3, which had you test, is r sub y equal to q sub z? Is p sub z equal to r sub x? And is q sub x equal to p sub y? And if all those things were true, right, then essentially the curl was 0 and we had a conservative vector field. So now you can see kind of where these things are coming from. Curl in its heart is trying to embed information about circulation. So how is a vector field trying to make, basically points or particles circulate at a particular point in space? So that's what curl does. And then we got a new kind of upgraded problem. Again, before in 16.3, we couldn't ask you for a three-dimensional vector field to show that it was conservative or not. We had to say, here's a conservative vector field, now go find me a potential function. But now with this information, we no longer have to tell you if it's conservative or not. We can just give you a three-dimensional vector field and say, hey, is this thing conservative? And if so, go out and find a potential function. So that being said, these sorts of problems using the fundamental theorem of line integrals are again fair game for this upcoming online test. So that's all the stuff about curl. The final thing here is about divergence. So with divergence, instead of taking the cross product, you're going to take the dot product. And this is the quantity that you get here. It's of course, the dot product is always a lot nicer than the cross product. And what we're going to be talking about in the in-class portion is, well, what does this mean, right? So I already told you that circulation or curl had something to do with circulation. And the question is, well, what does maybe divergence have to do with? All right. Any questions about anything in the pre-class video before we jump into the new stuff for today? Yes. So yeah, the question was, does divergence here relate to like divergence of an infinite series? And no, sadly it doesn't. So it's kind of hold these in two separate hands. Good question though. All right, any other questions? All right, let's go ahead and switch then. Oops. All right, so as I mentioned here, those are perfectly fine definitions and all that, but what are these things actually used for? So for divergence, again, divergence is a number, not a vector. So it's a number that comes out and it counts really how much is coming in or out at a point. So a positive divergence means that more is going out than in. And so if I was to go ahead and maybe here's a point, and suppose we have some vector field, and maybe the vectors around this point look something like this. Maybe there's some coming in, but you know, there's maybe more coming out. And again, this is all related to the magnitude of these vectors, so how long they are. So here's a case where I think that there is more going out, more vectors coming out of this point than there is coming in. Negative means that more is going in than out. Looks like I missed my H. So a different point over here. And again, maybe you have more vectors coming in. Doesn't need to necessarily be all of them, but more coming in than going out. And then 0 means, right, this is the same. So here's maybe an example of that. So the same amount going in is coming out. And again, these magnitudes of these vectors would need to be the same length. Okay, likewise, I told you curl is a collection of numbers. Again, it's a vector, so it's not a single number, but it's a collection of numbers that counts how much is rotating around at a point. So positive means that the rotation is in the counterclockwise direction. Negative means that the rotation is in the clockwise direction. And 0 means that there's no rotation. And really, maybe this should be better. 0 means that there's no like net rotation. I'll add in the word net here. So let's try to draw something here. So I think all of these vectors here would be trying to, kind of rotate around in this counterclockwise direction. And then let's have maybe one going in the opposite direction just to kind of show, again, they don't all need to agree, but overall there's more going in the counterclockwise direction than in the clockwise rotation, in the clockwise direction. Next up, we could say, again, majority are going to be going in the clockwise direction now. Maybe just one going against it in the counterclockwise direction. And then there's plenty of ways to draw no rotation. But I'll maybe just draw the same one as last time. And quite often when I'm thinking about the rotations, it's a little bit funny. I'm imagining kind of that there's like a wiffle ball here or something, and that these arrows are me swiping my hands. And the question is, what way is this wiffle ball gonna rotate? And so, of course, the ones, if my hand's just pushing into the wiffle ball, right, that's not gonna help it rotate at all. If there's the ones that are pushing under it, right, I think that when I push kind of down here, close to the bottom of it, right, it's gonna want to rotate in this, counterclockwise direction. And the ones that push on top of it, again, kind of if I'm just barely skimming it, are going to want to push it in the clockwise direction. And so again, those are going to cancel out. So that's what I'm thinking about with like these rotations, is like if there was literally something like swiping a ball from underneath or on top, right, how would this make it rotate? I play a decent amount of recreational ping pong and tennis and stuff like this. So I don't know, it helps me. So, but you may need to come up with your own analogies. All right. Any questions before we try to do a problem? Yeah.
So how do you know, like, mathematically that this is what it represents?
Well, I guess one way is certainly we can visualize these things, right? And if you do these enough times, right, at least that's a compelling argument. But yeah, in order to know that it works 100% of the time, yeah, you need to kind of tie this together with a better proof than I'm giving you right now. You can do that. And in fact, I do a little bit more of an in-depth proof of this in 16.8, the pre-class video for Stokes' theorem, because it relies on curl heavily. And so basically you need to break, when you're talking about rotation at a point, that's a tricky thing. So you first start out talking about rotation on a small rectangle, and then mathematics and especially calculus is all about letting limits go to zero, right? There's some limit or something like this. So you let these sides, this delta x and delta y, go to zero. And then so instead of calculating out the circulation around this entire small rectangle, you let that small rectangle go down to a point, maybe down here or something like this. And then you find out that the circulation, and again, you have to isolate your planes and all that sort of stuff. It's, I'm doing a very hand-wavy suggestion of a proof here, but this is essentially what it comes down to. But we'll at least be able to, with the examples that we do today, you'll at least not think I'm lying, I guess. You may not be 100% convinced. As a side note, so again, curl is this collection of numbers. Let me say, and add to this really quick, that in the x component, this is circulation in the YZ plane. Then in the second component, this is circulation in the XZ plane. And then finally, you have your circulation in the XY plane. At very least, again, at this point, I'm not giving you the full proof. I'm just telling you this is where all of the circulation information is stored for each plane. However, you should at least be able to look at what I've given you here And the fact that, right, this final component, Q sub X minus P sub Y, right, this had something to do with conservative in the XY plane, right? If this thing was equal to 0, then it was conservative in the XY plane. So it at least makes sense that this has, again, something to do with the circulation in the XY plane. And then you can also see all the partial derivatives, right? In the first one, this is our Y's and Z's, hence the circulation in the YZ plane. These ones are X's and Z's, hence the circulation in the XZ plane. And again, partial derivatives with respect to X and Y for the last one, hence the circulation in the XY plane. So I would like us to, given a picture of a vector field, we should be able to, at least by looking at it, determine if we have a positive or negative divergence, and if our curl is positive and negative in each component. And then, of course, it'd be nice to be able to verify. So I've given us also the equation for how I generated this vector field, and then we can actually do the calculation out and see if our guesses were correct. So first, though, use the picture to determine if the following value should be positive, negative, or 0. So I'm interested in the divergence of F at 1, 1. So I'm going to go to 1, 1. See, there's a 1 up here. I don't see a 1 on the other direction, so maybe there. So maybe there or so is around 1, 1. And when I look at divergence, there's a lot of information that, can kind of largely be ignored, right? So there's kind of these vectors up here and these vectors down here that are not really going into the point or out of the point. They're just missing the point. The only ones that are really kind of going in and out, I would say, are kind of these ones here based on this picture. And it's hard to see only with these couple. They all seem like they're kind of the same length. And so quite often I get a bit of a running start when I'm looking at these sorts of problems. And I look at this entire row sort of deal. I'm trying to gauge as I go from left to right, since that's the way these arrows are pointing. Again, the question is there more coming out or is there more going in? Are there longer vectors going into the point or are there longer vectors coming out of the point? And I would say as I move from left to right, it seems that the vectors on the right-hand side are getting longer than the vectors on the left-hand side. So I would guess that there's more coming out on the right-hand side than there is coming in on the left-hand side. So I'm going to guess that this is positive. So that's all my thoughts about divergence for this one. Let's go ahead and calculate out really quick and see if we get this correct. So again, divergence is supposed to be this del dot F. So a partial derivative with respect to X, a partial derivative with respect to Y. And since there are only two components, this seems like a reasonable place to stop. However, in the definition, right, there is this partial derivative with respect to Z, and it's okay if you want to include this in. It actually makes more sense. You'll need this when doing the cross product, but you can't include this in. But then that just means that your vector field, you need to write this as X plus Y, Y minus X. And if you're going to append a third component, there's nothing going on in the Z direction. So just 0 there. And so here, when you take your partial derivatives, you can see that I'm going to have partial derivative with respect to X of this first stuff, that's going to be 1. Partial derivative with respect to Y of the second stuff, that's also going to be 1. And partial derivative of 0 with respect to Z, that's going to be 0. And again, with a dot product, you add all these up. And so overall, I get 2. So again, a positive divergence means that there's more coming out at that point than there is coming in. So yes, this is it aligns with our guess. So I want to play the same sort of game here now with curl. So with curl, again with curl, I'm not so much interested in the ones that go straight into it. Right? If I'm imagining that there's a ball here or something like this, and I just jam my hand into that ball, it's not going to help the rotation whatsoever. It really has to do with what's going on above it, because these vectors right here You could also imagine maybe like a conveyor belt or something like this. If you have something kind of pushing in this direction, it's going to make your ball want to spin in this clockwise direction. And likewise, the stuff below it if you imagine swiping your hand below the ball, right, this is going to make it want to spin in a counterclockwise direction. So the question is, which is stronger? The vector is kind of above it or below it in this case. And again, in order to really kind of understand, because they look similar, I kind of look at the overall picture here. And I do see, it seems to me that the vectors that are higher up seem to be longer than the vectors that are lower down, right? So I think overall, the vectors on the top here are going to be winning out. And as they push, right, they're going to be trying to spin this in a clockwise direction. Let me pause here and make sure that I'm making sense. Are there any questions about this? Does this seem reasonable? Does anyone have another way that they're thinking about it besides swiping balls and thinking about how they're rotating? Conveyor belt or anything like that? All right, well, that's what I'll keep going with in the future then. All right, so I think this is going in a clockwise direction. Now notice that I'm not imagining there's going to be any circulation in anything except for the XY plane. After all, this entire picture, there's no Z's here, right? And so I'm kind of imagining that in my third component, which has to do with the rotation in the XY plane, that this is the piece that should be negative, aka, right, it's going in a clockwise direction. I don't think there's going to be much of anything going on with Z's, right? So the X Z plane and the Y Z plane, I don't think there's going to be any rotations going on there. Because again, this vector field doesn't even exist in the Z plane, either X, Z, or Y, Z. So I think we're going to have something like this. So let's go ahead and now calculate out. So curl of F. Again, we have a cross product. And we add what? X plus Y. Y minus X. And we didn't have a third component. Again, for cross products, you really need a 3x3 vector. You need a three-dimensional vector. And so you do have to really include the 0 here. So we're going to have stuff with I's minus stuff with J's plus stuff with K's. Excuse me. Crossing off that first row and first column here. We have partial derivative with respect to Y of 0 minus a partial derivative with respect to Z of something that doesn't have any Z's in it. Next up, partial derivative with respect to X of 0 minus partial derivative with respect to Z of something that doesn't have any Z's in it. And finally, first row, third column, partial derivative with respect to X of X minus Y, Y minus X, that's going to be -1, minus partial derivative with respect to Y of X plus Y, that's going to be 1. So this is saying there's not much circulation going on in the YZ plane or in the XZ plane, but it is going around in a clockwise direction in the XY plane. So that's how we can read our circulation vector here. And it agrees with what we were guessing. All right, well, I would like to give you guys a chance to try one of these. So I have a more interesting vector field, a little bit more difficult, but not a ton. So sine Y, cosine X, you get these interesting, like, I don't know, tide pool sort of things. So I'd like you to use the picture to determine if these things are positive, negative, or zero. Again, take a guess. And then can we use the equation to verify, right, if you guessed correctly? So it's at 3 pi over 2 comma pi, which my intent was for it to be right here. So kind of in the middle of one of these. So again, the goal is guess for divergence and curl, and then calculate. All right, let's bring this one back together. Tell me about your intuition on this. Let's start with divergence. Anyone have a feeling about should the divergence for this be positive, negative, or zero, and willing to share? Yeah?
Zero.
Why do you like zero?
Get the center of this circle. There's nothing going on.
Good. So there's really nothing coming in and nothing coming out, right? And so there's nothing to even cancel or whatnot. While the vector field seems to be kind of dancing around it, nothing's really kind of pushing particles into this point or out of this point. So I like it. I agree that divergence at this point ought to be equal to zero. And of course, when you calculate out and you take your partial derivative of your first component with respect to x, well, there's no x's, so you get zero. And you take the partial derivative of your second component with respect to y, well, there's no y's, so you get zero. So it's going to be 0 plus 0 plus 0. So it's an easy verification, right? Okay. Curl. Again, there's really nothing going on. It's not a three-dimensional vector field. And so we don't have z's. And so there's not going to be any rotation going on, in any of these z directions. But for our third component here, this is about rotation in the XY plane. And yeah, it looks like there's a lot of rotation in the XY plane. Anyone have a feeling is this should be positive or negative or zero? Over here.
Positive because everything's kind of going in it looks like we have more clock or counterclockwise than clockwise rotation.
Exactly, right? If I look at each one of these vectors that are kind of nearby, if I was just thinking about, swiping my hand in this direction, it's going to push in the counterclockwise direction. Or if I think about pushing my hand in this direction, again, it's going to push in the counterclockwise direction. Kind of everything is quite in agreement that, if there was a ball at this point, it should be spinning in this counterclockwise rotation. This one, for whatever reason, I imagine, it's actual water and that this is a leaf. So there's a leaf and it's going to be spinning in the counterclockwise rotation sort of deal. Anyway, so I agree with that guess, right? That this should be a positive number here, aka counterclockwise rotation. And as I walked around, I saw a lot of good work towards this. Again, we're going to need to calculate out a cross product here. So let's go ahead and do that. I's, j's, k's, partial with respect to x, partial with respect to y, partial with respect to z. We have what? Sine y, cosine x, and there's not a third component, so we'll just put 0. When we calculate this out, we'll have stuff with i's minus stuff with j's plus stuff with k's. And so crossing off our first row and first column here, we're going to have what? 0 minus 0. Crossing off our first row, second column, again, 0 minus 0, kind of as we guessed. And finally, as we calculate out and cross off our third column here, we're going to have what? Negative sine of x minus, sadly I need a little bit more room, partial derivative with respect to y of sine y, so that's going to be cosine y. So this one, unlike our last one, we didn't really have to plug in our specific point, right? So this one, it turns out 1, 1 wasn't special here. If you really have chosen any of these points, anywhere in this vector field, the claim is that the divergence and the curl, right, are always the same, that it didn't actually rely on what point you're at, 1, 1. In this case, it looks like it doesn't actually matter what point you're at for that divergence, because again, we didn't have to plug in 3 pi over 2 and pi into this whatsoever. So no matter what point you choose, although some of them may be a little bit harder to read, there's going to be the same amount coming in as there is going out anywhere in this vector field. However, we can find, well, at this point, it's kind of rotating around in the counterclockwise direction. There are certainly other places, for instance, maybe over here is very clear, where it'd be rotating around in the clockwise direction. So for rotation, it really does matter where you're at. And that's why we don't have a final answer yet. And we need to plug in the curl at the point 3 pi over 2, comma pi, just like I said. So at this point, the curl of f is going to be equal to 0, 0. And instead of x, I'm going to put 3 pi over 2. So I'm going to have sine of 3 pi over 2. So that's going to be what? Negative 1. So negative 1 is going to be positive 1. And then minus cosine of pi. So cosine of pi is negative 1. So minus a negative 1. And so we get 0, 0, 2. So indeed, a nice positive number here. But again, we can see that the curl really depended on where you were in this plane, unlike the divergence. Turns out, although some of them are harder to read, the divergence is 0 everywhere in this. All right, let me give you a quick definition and then I'll open the floor to any questions. So again, curl is to help measure rotation at a point. If the curl is equal to 0 at a point P, then we say that the fluid is free from rotation, and F is called irrotational. And then div, or divergence, represents the net rate of change of a mass of fluid or gas, right, flowing from points, X, Y, Z. So if the divergence of F equals 0, then there's no net change, and F is said to be incompressible. So formally, I've seen, I guess let's just peek at this example real quick, and then, like I said, I'll open it up to questions. But this would be a fine, like multiple choice or even a true false style question, right? That just, you need to know these definitions. But here's a vector field, right? Is this irrotational? Is it incompressible? Both? Neither? Right? They're fairly independent from one another, so it can be both, or it could be neither. It could be one or just the other, right? So anyway, that's some definitions. But any questions really about anything so far here? Overall, is this better or worse than spherical integration from Friday's class? Better. Okay, good. Good to end with a nicer subject, right? Before the exam. So that's good. All right, well, let's go ahead and do this example then. So here's our vector field. This one actually has some z's in it. That's nice. The pictures are horrible, right, if you have z's in it. So it's nice when we're visualizing vector fields to only have x's and y's. But in general, this works for 3 variable vector fields and all that sort of stuff. So it'd be good to do this here. So let's go ahead and double check, right? Again, this is just this definition: irrotational, incompressible are not on the formula sheet. So you do have to have these memorized. You just need to know, right, that this comes down to checking if the divergence is equal to 0 and if the curl is equal to 0. So let's go ahead and calculate out the divergence. So as I go across here, the first component, I'd be taking the partial derivative with respect to x. So I'm going to get -2. The second component, I'm going to take the partial derivative with respect to y. So I'm going to get -3. And then my final component, I'm going to take a partial derivative with respect to z. So I'm going to get 5. And then we're going to add all these up. And of course, we get 0. This is going a little bit fast, right? So if you're not comfortable with going this fast quite yet, I mean, you can quite literally partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z, dot with -2x, -3y, and 5z. Right, so there's our vector field. And so you're applying the partial derivative to each one of these and then summing them together. So if you'd like to take it a little more step by step, it's certainly fine. Hopefully by the time you get to the exam on Thursday, right, you're doing this a little bit faster though. This is perfectly fine. Okay, so we know that it's at least incompressible. Now let's check the curl. -2x, -3y, 5z. And the question is this 0 or not? So once you get one of these that's non-zero, you can stop, right? Because, I mean, if this is a 5 here, then it's certainly not 0, right? Again, exclusively 0 here. So let's do a partial derivative. We'll cross off the first row, first column. Partial derivative with respect to y of 5z. Well, there aren't any y's there. Minus a partial derivative with respect to z of -3y. Well, no z's there. So, okay, we need to continue. Partial derivative with respect to x of 5z. Partial derivative with respect to z of -2x. All right, it's looking like it might be irrotational as well. Last one. Partial derivative with respect to x of -3y. Again, no x's. Partial derivative with respect to y of -2x. No y's. So again, there's no rotation going on whatsoever. So irrotational. Again, when it says curl of f is equal to 0, this is really, should emphasize here, this is the 0 vector, right? Because curl is a vector. And so this really means it's the vector with zeros at each component. So you need all 3 to be equal to 0 for this to be irrotational. Oh, sorry, yes, question.
like positive and negative. If you have a vector of X, Y, and Z, what makes it positive and negative? Both terms positive, both terms are negative?
So yeah, the question was, it makes sense to say that a vector is zero by this definition, but how could you make sense of, if I wanted to say that a vector was positive or a vector was negative, is there a way to define such a thing? And then gave some suggestions for possible definitions. I haven't ever heard anyone try to define a positive vector or a negative vector. Your definitions seem reasonable, that, you know, if all the components of a vector are positive, then we could call it positive. Or if all the components of the vector were negative, we could call it negative. I just haven't ever heard that personally.
Talk about the definition of curl. It said positive means rotation counterclockwise, negative means rotation clockwise. So like, what does that mean?
Well, I mean, for any vector, right, it's most likely the case that the components are independent from one another, right? So when I'm talking about in this remark here, right, positive means that it's counterclockwise. So it's each component, right? So it's a collection of numbers. Each one of those numbers, when you look at it individually, right? So if I just looked at in the first component, let's suppose that there's a 5 there, right? Well, that means that in the YZ plane, if you were to just isolate and look at the vector field in only the YZ plane and strip away all the other vectors that are going on in space, right? It would look like that the vector field is trying to push particles around in a, well, it was 5, so that's going to be a counterclockwise rotation. Then if you were to look instead in maybe the XZ plane, right, and you were to take away everything, all the other vectors, and let's suppose you get -3 there, right? That means in the XZ plane, it wants to go in a clockwise direction. So it's a bit strange because, yeah, you have to isolate the specific ones, but yeah, so it's each individual component is what I was talking about here. Thank you for clarifying. That's a good question. All right. As I mentioned here, well, I didn't mention it, but I wrote it. Learn a carnival trick. And then we're going to, yeah, we already defined a few more things. So the carnival trick here doesn't get used a whole lot. Is this theorem. And it states that the divergence of the curl of F has to be equal to 0. So when you have a vector field F, as long as it's a reasonable vector field, that it makes sense to take partial derivatives of it and all that sort of stuff several times over, because you'll have to. Once you take the curl of F, you get a different vector field, right? But it's still a vector nonetheless. And then if you took the divergence of that, so you're actually, right after you take the divergence, you're getting a number out. If that has to be equal to 0. There's a proof in our textbook about this. And it's just, I mean, there's just a ton of partial derivatives. And it comes down to Clairaut's theorem, the fact that you can do these mixed partials are equal to one another. But otherwise, it's very dry and boring proof. But every once in a while, there can be questions like this that come up. And these make kind of good true-false questions. I have an example kind of below this, of this. And later on in 16.8 and 16.9, we're going to be talking about something called Stokes' theorem, which has to do with the curl, and divergence theorem is 16.9, which has to do with divergence. And this basically just says that there's not a very interesting way to combine Stokes and divergence theorem, that really they are best dealt in separate situations because you always just get 0. So, all right, silly question here. Your friend Ryan comes up to you and is like, whoa, you have to check out my awesome vector field. You know what? I bet you can't even figure out what it is. The only thing that I'll tell you is that the curl is equal to this. Shut Ryan up by finding his vector field, if it exists, or prove that Ryan is not being honest with us. This guy Ryan sounds like a jerk. Curl, right? It's made up of complicated stuff, right? If we go back to the pre-class video here and just stare at it really quick. Again, we would need our first component to be equal to R sub y minus Q sub z. And we would need our second component to be equal to P sub z minus R sub x. And we would need our third component to be equal to Q sub x minus P sub y. right? This would be very complicated to try to find a vector field that satisfies all of these things, especially because, right, these are simplified down so nicely. So one easy way you can check to see if this possibly even could be the curl of something is by applying the divergence to it, right? Because if this is the curl of some vector field, then if you apply the divergence to it, that you have to get 0. So if I apply the divergence to supposedly the curl of some vector field, according to the theorem above, we ought to get 0. So divergence. In the first component, we take a partial derivative with respect to x. In the second component, we take a partial derivative with respect to y. And in my third component, we take a partial derivative with respect to z. And we add all those up. And in this case, we do not get 0. This is not exclusively equal to 0. Depending on where you are in the XYZ plane, this is almost certainly not 0, right? So the answer is, well, yeah, no such vector field would exist. Now this question admittedly was a bit silly. Here's a way that you could ask it more reasonably on a quiz or test or exam or whatnot. True or false? There exists a vector field F such that the curl is equal to this. And again, if you apply the divergence to this and you find that that's not equal to 0, then the answer is going to be no.
They ask like this question, but they say at like negative 1, 0, -1, would it then be true?
So if they were to specify a point to this, then there's nothing stopping you from plugging that in there, right? So I mean, you could plug that in and see what that ended up yielding. So once you've evaluated at a point, it's kind of lost some of its meaning. It's kind of like back in calculus 1, you know, if you have a function f of x squared or something like f of x is x squared, right? And you say, well, we're going to take the derivative of that. You know, whether you take the derivative first and then plug in a point versus if you plug in a point, then take the derivative, right? You get very different results. And so by fixing yourself at a point, I mean, yeah, you can have the curl being equal to a specific point, a specific vector, pretty much no matter what, because once you take the divergence of a constant, right, you're just going to get zeros. So yes, that'll always be the case, that no matter what point you specify, if curl ends up being a constant vector, then of course the divergence of a constant vector is going to be 0. Yeah. One more time, biconditional. So we're saying if the divergence of the curl is equal to 0, then F is a vector field that has continuous second order partial derivatives. Oh, sorry, what do you mean? Yes. Sorry. Yeah. So yeah, if the divergence of the curl is equal to 0, then yes, such a vector field would exist. All right. So last problem here, not much time to spend, but this is another example of a fundamental theorem of line integrals style problem. Now with 3 variables. Maybe I'll at least get us through the first part here of find the values of alpha and beta so that F is conservative. So if we want a conservative vector field, that means that the curl has to be equal to 0. Well, we can calculate out the curl, I, J, K, partial with respect to X, with respect to Y, and with respect to Z, of, here's our yz plus alpha y plus 1, xz plus 3x plus beta z plus 2, and x, y minus y. Stuff with i's minus stuff with j's plus stuff with k's. And again, at the end, if this is going to be conservative, then we're going to need to get 0 out, each component. So crossing off the first row in the first column, partial derivative with respect to y of xy minus y, that's going to be x minus 1, minus partial derivative with respect to z of this stuff here. Let's see, I'm going to have x and plus beta. Those are the only ones that have z's in it. Next up, partial derivative with respect to x of, okay, x, y minus y is going to be, what, just y, minus partial derivative with respect to z of this bit here. That's just going to be y. So that one works out no matter what. And then finally, crossing off our first row and third column, partial derivative with respect to x of all this stuff. Let's see, we're going to have z plus 3 minus, and partial derivative with respect to y of this stuff, we're going to have z plus alpha. So you can see in order for this to work out, you're going to have that beta is going to be equal to -1. So when you minus a -1, that'll cancel out with the -1 there. The x's already perfectly cancel out, so that's nice. And likewise here, we're going to need to be having alpha equals 3. Z minus z will cancel out. 3 minus 3 will cancel out. So you'll need those two in order to make this conservative. Once you have a conservative vector field, you can apply it to the fundamental theorem of the fundamental theorem of line integrals. This is the exact same sort of stuff we did in 16.3, but again, we can do it now asking to show the conservative vector field thanks to the stuff we know about curl now. So I'll let you guys finish this one up. There are other homework problems similar to this, so you will be practicing more of your fundamental theorem of line integrals. And fundamental theorem of line integrals problems are, again, fair game for this upcoming test. So I'll stick around if you have any one-on-one questions, and I will post the solutions to this final problem here on D2L by 4 o'clock today. But yeah, otherwise, have a great rest of your day, and I'll see you guys on Wednesday.